Okay, it is a second attempt to demonstrate how to make spectra with spin polarization. Share screen. So the instructions are provided in the file. Now here I'm on the nurse. So the instructions are provided in the file bin advice spectra spin.u3. I know that we do not have anyone online, but let me share it in the chat line. Maybe it is recorded in a better way. So, as a first step, I did create the file input overlap. This file creates first and last orbital for alpha and first and last orbital for beta. Based on this file, the next script in the protocol, C, Control V, does the following. So it opens the file outcar and extracts the list of orbitals. So T. Now we do have energy pop down and energy pop. More energy pop. It is the same as a file states up when we were doing spin polarized DOS. So up to orbital 16, the orbitals are occupied. After they are empty. And if I look energy pop down, up to orbital 16, they are occupied. After they are empty. In some sense, the exercise I'm showing is only a reference point because the alpha and beta should be identical. Okay, let's look on the next step of the menu. So before running the scripts, one needs to swap module. We did before for the spectra. Right now it will go error because I have already done it. But this is needed to run different executables compiled with different compilers. Now, once again, a benefit of what we did is right now we do not need to manually extract list of orbitals. We can do it automatically by the script. So next, step number 4. So we take an executable from the directory spin OS for spin oscillator strengths and run the script. Select and run. So this script is very similar to what we did for oscillator strengths without spin. So it does read the wavecar file and creates, creates file oscillator strengths. This oscillator strengths is for spin up strengths. So if you noticed, instead of 2 and 0, it shows 1 and 1. So there are transitions with from orbitals that have population 1 because they're spin polarized. And also this file lists all transitions not only from occupied to unoccupied, but also from occupied to occupied and from unoccupied to unoccupied. So all possible transitions. While presenting this subject on the meeting, on the lecture, it is important that the one who is presenting tells what is the meaning of the numbers in this column. First, final orbital where we land, initial orbital where we start, the value of oscillator strength, transition energy. Here you see it is small, so it is in the infrared. Occupation of last, occupation of first, and then three components of the transition diagram. Okay, so let me have a glance on the manual once again. So we are done with step 4. Now we need to do step 5. It is the same, but there is a index down. There is an index down. So we execute a code that refers to the part of the wave car that deals with electrons of spin down projections. Running, exploring LS. And now we have oscillator strength down. Let's look more was down. There is another list of transitions, and they're quite or very, very close because here we do have equal number of electrons in the alpha and beta. So let's look on the manual once again. So step 6, explore availability of the generated files. So we already did it, but let's do it. Let's see, Control D. So we have oscillator strengths without subscript, which is up, oscillator strengths with subscript down for spin down. Now let's fix it. Let's step 7. Let's rename oscillator strengths with oscillator strengths up. So now we have appropriately labeled files. So the next step is a post-processing of the outcome of this calculation. We are looking onto absorption spectra, which means transitions from occupied to unoccupied. So this can be done by this command. So right now it shows from occupied to occupied, from this occupation 1 to 1. But we do need to extract such files that show transition from occupied to unoccupied. We can do it by this line. So grab from 1 to 0, oscillator strengths up, and then we will call it a different way. Okay, let's look inside. What was so it shows transitions from occupied to unoccupied. The values of oscillator strengths are smaller. The transition energies are in the UTV range. And it is what we need for our spectrum. Now let's do the same thing for the electrons with spin down projection. So grab from 1 to 0, oscillator strengths down. It looks quite similar. Or there are changes in maybe fifth digit, but it's numerical precision because alpha and beta here are identical. In the next video, I will show for triplet when alpha and beta will be very different. Okay, let's look on the manual once again. Okay, so after we are done with converting this os up, os down, we can do concatenate. So we can combine these two files into one file. Good. So you see the file OS strings is twice as bigger than OS up and OS down because it has just combination of them both. And basically, this is the last step. Now I can treat the oscillator strength file in the same way as we were doing before. So WC was strings 154 lines. Now I'm running spectrum IP. So this code converts the list of transitions into continuous absorption line. Number of transitions was the result 154. 1.4. Minimal, maximal energy difference. I'll start from positive number close to 0. I will end, let's say, at 8 electron volts in the UV range because this molecule is transparent for human eye. It is expected to absorb only in UV. And width of each line is 3.0. Number of homo 16. Enter. Done. After this, I have plus minus OT head. There is a file spectrum. I can convert file spectrum into the graphical file by typing new word or SPE1. So this script, as we remember, just puts this content of this file graphically. Now we do have this SPE1. Let's do S2PD SPE. Yes. As a result, we have a file SPE1 PDF. And now I want to send this PDF file to the Photon and then extract Photon from Photon to my local computer. So on the local computer, singlet neutral, I created a directory singlet neutral optimize. Before starting this meeting, I did have create an appropriate subdirectory on the Photon, singlet neutral optimized. Now I'm clicking on a different tab, returning to NERSC, and I'm doing SCP, everything that ends with PDF, user, server, typing password, file is transferred. On a local computer, SCP from photon to local computer. Typing password. Transfer. Now I may want to open this file. Open LAB11 singlet neutral optimized. So it has absorption in 4.5 because bigger than 3 EV, which would be for bulk titanium dioxide, because this molecule is confined. Okay. Let me show few more. So the video, important part of the video ends here. Obligatory part of the video ends here. Now I will show a couple of extras, but they are optional. They're not needed. If you're in a rush, you can stop watching this video and go to the next one. So there is a script prog spectra nanometers. So let's explore it. Plot spectral nanometers. So experimentalists make absorption spectra as function of nanometers. And there we use, instead of 2 and 3, we use 1 and 3. The script converts, when we were running spectrum underscore IMP3, it creates additional column which shows transition energies in nanometers. And now this running the script, we have the SPE underscore NM. SPEFWR SPE underscore nanometers. And I want to send this file to Photon first. And then from Photon, I want to download it to the local computer. So if I'm opening this file, I see that the spectrum looks a little different. So it is inverted. It has non-zero values at small values of nanometers. So nanometers, the scale of wavelengths is inverse to energy. When energy increases, wavelengths decreases. So we have a peak with a height of maybe 12, and in the electron volts in energy range, it was at 4.5 electron volts. If you look in the range of nanometers, it appears at around 350. So the conversion factor wavelengths equals 1242 divided by electron volts. So if we do 1242 divided by 4, it will be about 300. And then other peaks have same pattern of intensities, but they go in the opposite direction. So if you want to talk to experimentalists, it will be most appropriate way. So this range is UV, then from approximately 400 to 700 is visible, and then the rest is infrared. Okay, and you can definitely stop watching right now. I will add one super extra, which will be not demanded for the classic homework. I just think it will be helpful. to those who try to use this skill into in the research. So one may want to decompose contributions to the spectra to contributions from alpha and from beta. So the combined thing is our spectrum. So copy spectrum into spectrum spectrum underscore. Now I'm removing spectrum. I'm removing weighted strengths, and I'm doing check was up into oscillator strengths. So right now oscillator strengths contains only transitions up. And now I'm redoing this conversion of the discrete lines into continuous file. Spectrum 3, 154, 1, 8.05, 16, done. Let's make a T file. So I am converting the moving, renaming create file spectrum into spectrum underscore up. Now I'm removing oscillator strengths and recreating down into oscillator strengths. We see OS strengths and running conversion from discrete to continuous. 4, 1, 8, 1, 0, 0. Right. Let's run over because it doesn't like when I do backspace. 4. 1, 5, 16, done. Now I do have spectrum once again, but it's a different spectrum. I want to rename it in the spectrum into spectrum underscore down. Now let me watch this script that I'm going to use. So it plots spectrum up, spectrum down, and spectrum complete together. So, and it will call SPE underscore spin EV. So what? OT tab. So there is a SPE spin EV. I am converting PS to PVWR. SPE underscore spin this. And after this, I want to send all files with in PDF format from here to photo. And then on the local computer, I might want to download this file. and I may want to open. So you see that you see nothing. They block each other because they are absolutely identical. So spin up, spin down, and spin complete just give the same signal. And you noticed I multiplied spectrum up and spectrum down twice so that normalization will work identical way. Otherwise, they will be twice as lower, but purple and green would block each other anyway. So this video is completely useless. It just creates a reference point of how singlet spectrum looks like in presence of spin. I think it is prudent to stop the video right now and redo the same steps for the triplet state of the same mode. I'm going to stop and restart, and you're welcome to watch the second video.